Bismillahirrahmanirrahim. BS Physics, Semester 1, Mechanics, Course Code 1103. First of all, I'm talking with you, Rashmat Ali, Assistant Professor of Physics, Government Khajafri, Postgraduate College, Demia Khan. Before starting the lecture, I welcome back to your studies after the midterm exam. I hope you have done well in the midterm exam and now you are fully concentrated for the forthcoming final term exams. Keep in test. Today's lecture is we have started chapter 6, circular motion and other applications of Newton's laws. The name of chapter. I have divided this chapter in different lectures. The first lecture of this chapter is uniform and non-uniform circular motion and the Newton's laws. The material of this lecture has been taken from two books. One of the Physics for Scientists and Engineers by Survey Javid. Another is Fundamentals of Physics by Harold and Resnick and Agile Walker. This is the main diagram of the chapter as the motion chapter is related to the circular motion. The circular swing shown here. Main topic of the chapter, Newton's, we have chosen the three topics for this lecture. Newton's second law applied to the circular motion, uniform circular motion, then the non-uniform circular motion, motion in accelerated frames. So first of all, we start Newton's second law applied to the uniform circular motion. First of all, it is necessary to know about the circular motion, then uniform circular motion, then afterwards we apply the Newton's second law to the circular motion. So circular motion, the motion of a body in a circle or a curved path is called circular motion. There are two cases for the circular motion. One is the uniform circular motion, another is non-uniform circular motion. Uniform circular motion, circular motion with uniform speed is called uniform circular motion. Means if a body is moving with uniform speed in a circle, we call it this circular motion as a uniform circular motion. We can see a body of mass m is tied with a string. Another end of the string is caught by a person's hand. It is whirled in a circular path of radius r and in a clockwise direction. So, when body moves in a circular path, whether its speed is constant, the velocity of the body changes from point to point. The velocity is always directed along the tangent to the circle Since the velocity is changing, so there must be acceleration. As we know, acceleration, the rate of change of velocity with time, is called acceleration. So, in this case, we study the acceleration due to circular motion That acceleration is known as centripetal acceleration. In typical way, we study the centripetal acceleration as the acceleration of a body moving with uniform velocity, uniform speed, v in a circle of radius r directed towards the center of the circle is called centripetal acceleration. So, we have studied this relation too in the previous classes. AC means centripetal acceleration. Mathematically, we can write it as v square over r. Here, AC is also can be written as AR. AC C is subscription for centripetal and R is subscription for radius and radial acceleration. It is to be noted that the acceleration is always directed towards the radius, along the radius toward the center of circle, whereas velocity is along the tangent, so acceleration is perpendicular to the velocity. We can study this in detail too. Consider a ball of mass m that is tied to a string of length r and is being whirled at a constant speed in a horizontal circular path as in figure. Weight is supported by the frictionless table. According to Newton's first law, the ball tends to move in a straight line. However, the spring prevents the motion along the straight line, but by exerting on the ball a radial force Fr that makes it to follow the circular path. This force is directed along the string toward the center of the circle as shown in a figure. If we apply the Newton's second law along the radial direction, the net force causing the centripetal acceleration can be written as, since we know sigma F, the sum of all the forces acting on the body of mass m, and the c is the acceleration. So m is into v square over c. It's a centripetal acceleration. Centripetal force is shown in this diagram directed toward the center of the circle. What happens if the string breaks? Means, as we have discussed, the force, according to the first law, the force is tending to move it along the straight line, but the centripetal force tends to move it in a circular path. So when the centripetal force becomes zero, reduces or string breaks, then the ball moves along the tangent to the circle. A force causing a centripetal acceleration acts towards the center of the circle and causes a change in the direction of velocity vector. If the force should vanish, then the object would no longer move it in its circular path. Instead, it would move along a straight line path that is tangent to the circle. Second small article of this lecture is non-uniform circular motion. As we know, the uniform circular motion means when a body moves in a circle with uniform speed. That means velocity, whether it is changing, it does not affect the uniform motion. But when we say that uniform, non-uniform circular motion means when a body moves with varying speed or varying direction of velocity, then we can say it the motion is non-uniform circular motion. If a particle moves with varying speed in a circular path, there are two components of acceleration, a radial component AR and a tangential component AT. In vector form, we can write it as the boldface is used here. Even in handwriting, we can put the arrow above accelerations. A is equal to AR plus AT, where R is the radial subscription and T is tangential subscription. There are two accelerations because these accelerations are produced under the action of force. So there must be two forces. If we multiply the mass m on both sides of the above equation, A equal to AR plus AT, then we get the force sigma F, sum of forces, sigma FR, sigma FT. So, from the diagram, we can see here, one force is FR directed toward the center, another force is FT along the tangent to the circle. The resultant of both is sigma F, that is neither directed toward the center nor along the tangent. The vector FR is directed towards the center of the circle and is perpendicular and responsible for the centripetal acceleration. The vector FT, tangent to the circle, is responsible for the tangential acceleration, which represents a change in the speed of the particle with time. Now, the short article, the types of forces. There are two types of forces. One of the real force, another is fictitious force. What is real force? The force which can easily be observed are called real forces. The forces arise due to the interaction between the two objects. Suppose force between Earth and the objects, we can observe the gravitational force, the force between the two charged particles. Similarly, the force of attraction or repulsion between two magnet pole pieces. These forces are basically real forces. The second type is the fictitious force. These are basically invisible forces acting on the body, we cannot directly observe these forces. These forces are produced by indirect interaction due to change in direction of velocity. So, examples of fictitious forces are coriolis force, apparent forces due to the accelerated frames. So many examples will be there. We see a circular, whether zigzag, even complicated ride. If we can imagine the people sitting in the cars that are moving in circular path, they don't fall even when they are inverted and at the peak of the circle. So the fictitious forces are present there. Now, in another article, motion in an accelerated frames. First of all, we know the frame and then its types. Frame is a three-dimensional structure relative to which measurements are taken. Is a frame of reference. We can even use the name the frame of reference. Frames has the two types. One is the inertial and another is non-inertial frame. Inertial means when body has zero acceleration, means when a body is at rest or moves with uniform velocity. In other words, when net force acting on the body is zero, the body is in inertial frame of reference. If a body has some acceleration, means velocity is increasing or decreasing, then the frame of reference would be called an accelerated frame of reference. What happens when accelerated frames move? Then consider first example. Suppose a hockey table, just like table tennis, is placed on a train, moving train. The train is moving with constant velocity. If a train is moving with constant velocity, it means it is an inertial frame of reference, as we have defined it. So, a table on the train, moving train, table on the moving train with uniform velocity will be inertial frame of reference too. So anything placed on the table will be at rest and remains at rest. This is the first clause of the Newton's first law. So the Newton's first law is observed because the table is at rest and anything, any puck, any substance placed on the table is also at rest, and it will remain at rest. The accelerating train is not an inertial frame. If the velocity increases of the train or velocity decreases, then it becomes non-inertial frame of reference. Then according to the observer on the train, there appears an invisible force on the puck on any substance due to which it accelerates from rest towards the back of the train. We observe normally when we travel on the buses, trains, something placed, even we have removed our shoes from when it is moving. After a long distance, we will find our removed shoes on the back side of inner of the bus, because even the bus is moving with uniform velocity. The bodies move towards the free bodies move towards the back of the train or box. So is happening here. Any substance on the table of the train moves back from rest. This violates the Newton's first law because it must be at rest. As an observer on the accelerating train, the Newton's second law can be applied to the puck, to any substance on the table. This apparent force is a fictitious force because it is due to the accelerated frame. The second example, to know about the fictitious force and motion of the objects in accelerated frame, consider a car is traveling along a highway at a high speed and approaching a curve exit ramp. You know the exit ramp. Ramp means something inclined plane, and exit means escaping from the plane. The car takes a sharp left turn onto the ramp. A person sitting on the passenger slides towards the right. Turn is taken to the right, and person moves towards left. Or if turn is taken to the left, then person slides towards the right and hits the door. A fictitious force due to the acceleration associated with the change in direction of velocity pushes towards the right. The force of friction prevents to slide to the right. If the force of friction is not sufficiently great to allow the passengers to travel along the circular path, then the body will skid out away from the center of the circle. The force acting and moving seen nowhere is the fictitious force, and this fictitious force is due to the accelerated frame. So, consider third example. Two persons are sitting on the opposite sides of a table, rotating circular platform. A person tries to throw the ball towards the other at t equal to 0. Suppose this is the diagram shown here. We can see the time is t equal to 0. At this time, a ball, green coloring, is thrown towards the other side, apparent at t equal to 0. Since the table is rotating and its speed is varying, so at the final time, Tf, the friend for the friend, and the Tf for yourself or myself, then what happens on the ball on this accelerating frame? After time, if Tf, when the ball crosses the inertial frame, the ball, according to Newton's inertial law, inertial frame of reference, the ball follows the straight line. By the Newtons in the non-inertial frame, the ball follows a curvature. If we say that the tabletop is inertial, then it must follow the straight line as shown in this figure. If it is in accelerated frame, then the ball must follow the curved path as shown in the second figure. The curved path followed is due to the fictitious force. Fictitious force can not be real force, but they can have a real effects. We don't know, directly observe the cause of a fictitious force, but its effect we can easily observe. An object on the dashboard of accelerating car really slides off. It accelerates, is pressed in. We can see the merry-go-round as the main picture of this chapter is merry-go-round type of swing. We push towards the acceleration is pressed in it outside. The coriolis force due to the rotation of Earth is responsible for the rotations of hurricanes and for large-scale ocean currents, cyclones that are produced due to the coriolis forces. In this way, the chapter ends. The chapter portion of this chapter is going to end. Thanks for listening and focusing with patience. Allah bless you all.